So today we're going to do section 7.5, or at least that's what we're going to get started. And basically, this is about solving trig equations. Okay. Now, we've actually done a couple of these so far. And the key thing here is figuring out how many solutions or what the solutions look like in terms of where our domain is. And let me give you an example here. So let's say we want to solve for x, and x is going to be between 0 and 2 pi. So let's find all values of x which make this true between 0 and 2 pi. Let's say we're trying to solve just cosine of x equals 0. Now, we've actually seen this, we've looked at a couple different ways. By the way, all these solving trig equations, all be solved in radians. I think I've mentioned that before, but most of the time we're dealing in 7.5, we're dealing with radians. So solve for x. And if we're going to do this by hand, we would think to the unit circle. And the fact that every point on the unit circle is cosine theta, comma, sine theta. So if we're asking when is cosine equal to 0, that's when the first coordinate on the unit circle is equal to 0. So here's one point where cosine is 0. Here's another point where cosine is 0. Right? First coordinate. And if we're talking about between 0 and 2 pi, we get to this point when x is pi over 2. And we're at this point when x is 3 pi over 2. We'll probably round those to 2 decimal places when you put them in to your answer for Moodle, I think. Right. So that's thinking through the unit circle. Now, we actually saw that before, earlier in this class. Remember that all of the angles where cosine theta is equal to 0, it could have been negative pi over 2, negative 3 pi over 2, positive pi over 2. Hopefully remember doing this, 3 pi over 2, 5 pi over 2, and so on and so forth. Or in other words, some integer times pi plus pi over 2, whatever that is. Remember that. So we actually kind of dealt with this using that kind of situation. And this is the best thing. When we can get our trig function equal to 0 and then we know answers, that's fantastic. Let me give you another way you could have solved this. And this was the way that we could have used without turning to the unit circle. I should say, without turning a lot to the unit circle. We could have said, well, if cosine of x is equal to 0, then we should set x to be inverse cosine of 0. So this is another option of solving. And so we could have picked up our calculator and done inverse cosine of 0. And that gives me 1.57, which is pi over 2, the decimal version of pi over 2. On my calculator. Now, this is where the rubber meets the rubber. Okay? If you're using your calculator in this format over here, we have to realize that our calculator with inverse cosine gave us answers between 0 and pi. Remember that? So when we did the inverse trig functions, we saw that we got answers between angle 0 and angle pi. And because of the way cosine works, because that cosine x or cosine theta is the first coordinate, what I need to do is I need to also project straight down across the x-axis, and that'll give me a second point. All right? And that gives me 3 pi over 2. We okay with that? So if we project that point across the x-axis, we get another point for the answer. And then if you wanted to, you could actually, like I said earlier, you get infinitely many values by just adding 2 pi to everything over and over and over again. Does that make sense? So these are the kind of the 2 basic techniques that we're going to use over and over again. Once we get it down to cosine of something is equal to a number. One is we're going to think about how this works with the unit circle. Another technique is we'll use inverse cosine and we'll get our other points on the unit circle by projecting across the x-axis in the case of cosine, or projecting across the y-axis in the case of sine. Does that make sense? So it's going to be inverse cosine using inverse cosine, or using our knowledge about the unit circle. Okay. So that's going to be kind of like the end steps in all of these. All right. In all of these, the end steps is going to be knowing what we know about the unit circle to find our angles, or using inverse cosine to find the angles. Okay. Now, in the other steps, what we would like to have is we would like to have equations like this. Cosine of an angle is equal to some number. All right. So in general, when we solve trig equations, we treat the trig function like a variable. We want to isolate that on one side. That's what I mean by treat it like a variable. Get the trig function equal to a number. So isolate that variable just like we normally would. And then solve using inverse trig function or the unit circle knowledge. That makes sense? That's basically what it's going to be. Now, this is generally speaking. There's going to be some tricks in this number two. There's going to be, in fact, quite a lot of tricks. All of that identity stuff that we saw in 7.1, 7.2, 7.3, 7.4, any of that could be employed here to try to get our trig function equal to a number. We'll see that. That's sort of the most advanced stuff. Okay. Is that right? So any of that stuff can be employed for number two, for step two then. So let's do a couple of examples of solving trig equations. Maybe I'll start with some stuff that we already know. Okay. So let's we want to solve for theta, where theta is between 0 and 2 pi. And let's take sine of theta. No, I'm sorry. I miswrote that. Sine of 4 theta is equal to 0. What's that sine? So sine 4 theta is equal to 0. Now, we've seen this before. I'm going to use, well, let me take a step back. Okay. Sine of 4 theta equal to 0. We've seen these types of functions already. Okay. We're going to treat the trig function like a variable. And we want to get our trig function is equal to a number. We already have that. So we're already basically done with step 2 here. So we're gonna solve these either using unit circle knowledge or inverse trig function knowledge. And what I'm going to do is I'm going to use unit circle knowledge. Unit circle says that if sine of an angle is equal to 0, sine is the second coordinate. So that puts us here or here. That puts us at 0 and pi, but also we could go around to 2 pi, to 3 pi, to 4 pi, 5 pi, all that stuff. So unit circle knowledge tells me that any k times pi, where k is an integer, will work. And I'm going to do this the exact same way I did last time we solved equations like this. I'm just going to list out all of my possible outcomes, at least for a while. And then I'm going to say, well, let's divide them all by 4, because that 4 theta being equal to one of those angles means that theta has to be equal to one of those angles divided by 4. Now, here's where it gets maybe a little bit tricky. I want my theta to be numbers between 0 and 2 pi. That means these negatives won't count. So I'm going to start here. And I actually haven't gotten up to 2 pi yet. 5 pi over 4 is still under 2 pi, isn't it? So that tells me that I need to go further. I need to go 6 pi over 4 and 7 pi over 4. And once I get to 8 pi over 4, 8 pi over 4 will be 2 pi. Does that make sense? Now, this one does not, I purposely left off the equal sign here. Notice that. So I will not count 8 pi over 4, but I'll have to go up to 7 pi over 4. And at 8 pi over 4, I can stop. Does that make sense? Stop right before then. So if I'm writing down the answers that are between 0 and 2 pi, I'm going to start at 0 and then do pi over 4 and then do 2 pi over 4. I'll reduce that. And then do 3 pi over 4. And then do 4 pi over 4. That's just pi. And then do 5 pi over 4. And then do 6 pi over 4. And then do 7 pi over 4. And then at 8 pi over 4, we hit 2 pi. And so I can stop at 7 pi over 4. That's a lot of answers. but that's what they are. That makes sense? So when we have it equal to 0, I like using the unit circle. Okay. When we have sine of something equal to 0 or cosine of something equal to 0, I like using the unit circle. Let's do another. Let's basically do the same thing. We're going to solve for some variable. Again, we'll use theta again. And we'll go from 0 to 2 pi. Let's say we have 2 times cosine theta is equal to the square root of 3. All right, so I'm going to treat my trig function like a variable, or I'm trying to isolate that trig function, right? I want to isolate that trig function, get trig function equal to a number. In this case, that means we have to divide both sides by 2. So that will give me cosine of theta is equal to the square root of 3 over 2. Now, if we know unit circle well enough, we can actually do this via the unit circle. Okay, if we know the unit circle. Remember, root 3 over 2 comma 1/2 was one of the points under the unit circle. But most people don't have the unit circle memorized to that degree. So what I'm going to do is I'm just going to do inverse cosine on my calculator. So inverse cosine of the square root of 3 divided by 2. I got a value that, well, let me just say it this way. It's actually pi over 6, but it's about 0.5236 or something. So I'm gonna this right is about 0.52. Is that okay? Round 2 decimal places. All right. So I'm going to call it pi over 6. In Moodle, you'll write it as 0.52. All right. Moodle, you write it as 0.52. But I'm going to call it pi over 6 just to make our lives a little bit easier thinking through this. So the question is, that gave me one angle when I did inverse cosine. And we're always going to get that. Inverse cosine is going to give me an angle between angle 0 and angle pi. So I got pi over 6, which is essentially you know, this point right there. The other angle that's going to give me a cosine of square root of 3/2 it's going to be what I get when I project that point across the x-axis. How do I project across the x-axis on the unit circle? In other words, how can I find that angle? But you have an idea.
Would you add pi?
Well, if I added pi, I'd get this one straight across. It'd go. Adding pi essentially projects through the origin. And that works fine when I'm doing that one, right? But when I'm doing that one, I can't just add pi. And so the way you project across the x-axis, angle-wise, is you take your all the way around 2 pi, and then you subtract whatever angle you're getting. Okay? So in general, you take 2 pi minus the angle that you're given. So I'm just going to do that. And I would suggest when you do this on your homework or whatever, don't use the rounded version of 0.52. Use whatever the actual calculator spit out. So if you did 2 pi minus your answer, you guys know how to do that? 2 pi minus second, and then the negative button. That'll give you 2 pi minus your answer. And you get about 5.76. So my answers are that theta is either close to about 0.52 or theta is about 5.76. Let's do another, similar to that. Let's say we have four times sine of theta plus 7 is equal to 6. I want you to use the inverse sign to get the first answer here. Okay, and then we'll get the second answer. Together. So try to solve this using inverse sign and get an answer, a single answer. All right. So hopefully everybody has done this. We get sine theta is equal to -1/4 when we sort of isolate the sine theta. Okay, that's the biggest thing. So we isolate the sine theta, and then we go inverse sine on both sides. Now that's going to give me an answer, but it's going to give me an answer between -π/2 and +π/2. If you remember about sine inverse or arc sine, gives me answers on the right-hand side of the unit circle. And so what answer that my calculator gives is -0.25, roughly. And this is not a nice angle. This is not like π/6 or anything like that. So about -0.25. By the way, that puts me, I don't know, at this point here on the unit circle. Notice that my answers need to be between 0 and 2π. That answer is not. That answer is below 0. It's negative. So if I want the positive version of that answer, what I would do is I'd simply add 2π. And I'm gonna do that on my calculator. Again, I'm just gonna add 2 pi to my answer. So that's about 6.03. Everybody follow that? That's the same point, but just with a positive version. Everybody see what I just did? I started at the negative 0.25 angle. I added 2 pi and I went all the way around and got to the same point. Trying to use different color markers, things like that to show. Now, how do I get my other point? And first off, where is my other point? Is my other point going to be in the first quadrant, second quadrant, or the third quadrant for sine? Well, since we're dealing with inverse sine, the other point is going to have the same y value on the unit circle. Does that make sense? Same y value on the unit circle. So I need to project across the y-axis to get to this blue point. All right? So the second angle is found by projecting across the y-axis on unit circle. How am I going to find that one? When we projected across the x-axis, we did 2 pi minus the angle, right? Over with cosine, right? Here we're dealing with sine, so I need to project across the y-axis. How am I going to figure that out? Well, think about what this is, what this blue dot represents. It represents going pi units and then plus a little more, right? How much more is that little more? Well, it's the same amount as whatever this was. Okay. That, in the negative sense, was negative 0.25. So I'm going to go, essentially, I want to do pi plus about that 0.25. Okay. Now, so I'm going to take pi, and since I know this comes out as a negative, I'm going to subtract that angle. that make sense? So I'm going to take do that, which is about 3.39. Everybody okay with that? Right, see where I'm getting at? I like to have a unit circle drawing for this exact reason. Okay? Because oftentimes, when you do the inverse sine, or when you do an inverse cosine, or when you do an inverse tangent, you end up getting a point, and you have to figure out a second point. Or maybe even you have to figure out a different version of that first point on the unit circle. And if you had the easy way, if you need a same version of the same point, just add 2 pi. That's easy to do. Go 360 degrees around, be at the same point. But if you're projecting across the y-axis, pi minus whatever value you got out is a good way to project across the y-axis. 2 pi minus whatever value you got out. Good way to project across the x-axis. Interesting. Any questions about that? Go for it.
Would it, if the original, like the 0.25 came out positive, if it was on the top, would you still use that same format, pi minus the inverse?
Yeah, so let's check it out. Let's see if, in fact, that was my next one. So let's say that we're doing a question and we're going to solve for, I'll use x this time. Most of the questions, I think, have variable x as the variable inside the cosine or inside the sine argument. So let's say we have 3 sine of x plus 5 is equal to 7. I want you to figure out your first answer, and then if you can, figure out your second answer by thinking through what's happening on the unit circle. Alright, so let's check this one out. As you're solving this, the solving should be fairly straightforward for x anyways, or for sine x. We go sine of x is equal to 2/3. And so when you do your inverse sine of 2/3, I forgot even what we got here. 0.73 roughly. Okay. .73 is somewhere, well, it's in the first quadrant. Okay. It's in the first quadrant. So this is one of my solutions. This is one of my solutions. Because it's between 0 and 2 pi. The other solution we get by projecting across, well, again, everybody understand why I'm doing the y-axis because of the sine, right? Does that make sense? So we're doing sine is equal to a number, and sine is the y-coordinate or the second coordinate on the unit circle. So we're projecting across So the question is, can I do the same technique where I take pi minus the angle? Sure does look like that, doesn't it? I have an angle over here. Remember my original angle. I'm using points to save on my lines here, but really, we're talking about the angle that gave us those points, right? So my original angle that I found is over here. It's whatever this rotational measurement is. So if I start at pi and then go back that rotational angle, is going to be pi minus whatever that angle is, right? So projecting across the y-axis, when I get a positive theta, is the same. And that's about 2.41. Roughly 2.4. So those are my two solutions between 0 and pi. Or 0, yes, they're both between 0 and pi, but they're the only solutions between 0 and 2 pi. My original. idea. By the way, for inverse sine, you never get a negative number, right? I think that I misspoke. For inverse sine, sometimes you get a negative number, sometimes you get positive. For inverse cosine, you never get a negative because cosine is always defined on the upper half of the circle. Questions about that? Now, let me do a very quick problem. Let's say I have cosine of x. Oh, I'm gonna solve for x between 0 and 2 pi. And we have cosine of x is equal to 3. Would you try solving that? Well, you can either think of this through the calculator or through thinking through the unit circle. What happens here? When does cosine equal to 3 on the unit circle? For what angle? And you say, well, never. I hope you say never. The cosine is limited on the unit circle to have an output between -1 and +1. So the cosine is always limited outputs between -1 and +1. And if you try to use inverse cosine, you get an error. You get a domain error for your inverse cosine. So what we're saying here is that there's no x to make this true. There's no x that's going to make that work. And if you end up with that, you will simply write D and E for does not exist in Moodle. Is that all right? So if you end up with one that does not work, then you just use D and E for does not exist. All right, let's go to another. We haven't done this yet, so let's take 2 times tangent of x and set that equal to 6, I guess. We're gonna do the same techniques that we've been using. We isolate the trig function. Here we divide both sides by 2, and we get tangent of x is equal to 6. I'm sorry, tangent of x is 6 over 2, so that's equal to 3. By the way, you might think of the last problem we did and said, oh, 3 was not a good output for cosine. 3 is also not a very good output for sine. That would not exist if it were sine. But tangent, that's fine. You can have tangent of something equal to 3. Okay. So it's perfectly fine to do inverse tangent of 3. And it gives you about a 1.25. By the way, 1.25, that's obviously a positive angle. What quadrant is that in?
1.
Yeah, it's in the first quadrant. Remember, first quadrant's between 0 and pi over 2. Pi over 2 is about 1.57. So we're somewhere here where my angle 1.25, roughly 1.25, that's my angle there. Okay, that's giving me tangent to be 3. Now, what's the other angle on the unit circle that's going to give me a tangent of 3? Well, let me say it this way. Which quadrant is it going to be in?
Would be 3.
3, exactly. Tangent is sine over cosine. So the tangent relationship is a projection through the origin. All right? Because it's like having positive cosine and positive sine. If I do a tangent, if I had a negative cosine and a negative sine, I would get the same thing. So whenever we're talking about tangent, we're going to project through the origin. And that's the easiest projection there is. You add pi to something. Okay? So my other angle is going to be pi plus the 1.25, or 1.25 plus pi, either way. We'll write that. About 4.39. By the way, if you ever have any doubt about this, you can always check to make sure you got the right answer. Just plug in 4.39 into the tangent and see that that gives you about a 3. Obviously, it's a rounded number, so it's not going to be precise, but if I do tangent of 4.39, I should get almost 3. Again, the rounding is going to throw you off a little bit, but. So with cosine, we have to project across the x-axis. With sine, we have to project across the y-axis. With tangent, we have to project through the origin. And I always think projecting through the origin is the easiest one because you just add pi and you're good to go. Projecting across the x-axis is 2 pi minus the angle projecting across the y-axis is gonna be pi minus the angle. Right? Again, if you have a unit circle handy, just kind of to draw, sketch it out. It's nice sometimes to sketch that out, see if you're on the right page. Let's do one more like that. So we're gonna solve for a value of x between 0 and 2 pi. Let's take 3 times tangent of x plus 7 is equal to 5. There. Solve that one on your own. All right, let's go through this. So I trust that you can solve down to tangent of x is equal to negative 2/3. Subtract 7 from both sides, divide by 3. So we subtract 7 from both sides, divide by 3, and we get tangent of x is equal to negative 2/3. Now, when I did my inverse tangent, it gave me back about a negative 0.59, which means we're in the fourth quadrant. Hopefully everybody sees we're in the fourth quadrant, right? Now, that is not an angle between 0 and 2 pi. I'm going to get the actual two values, one of which I can project across the origin, project through the origin. So I can get pi plus negative 0.59. So that angle is about 2.55. So that's this angle. That's that x. And the other angle, well, you can do this one of two ways. You could take your original blue and add 2 pi to it, get back at the same point. Or you could take the green and add another pi to that, right? Because we just added pi once, add pi again. So either way is fine, but here's what I'm gonna get. Also add 2 pi to get back same angle. So I'm gonna add 2 pi to that x. And I got about 5.70 rounded to 2 decimal places. So if you get a negative value and I want a positive value, you just add 2 pi. Okay, all right with that? So again, we've done a lot of cosine, sine, tangents, and basically it's sine of this angle is equal to a number, cosine of this angle is equal to a number, tangent of this angle is equal to a number once I isolate the trig function. Okay. Now, there are a couple of other tricks that we can do. And by a couple of other tricks, there's quite a lot, in fact. It's all the stuff we've done from 7.1 through 7.4 with identity stuff. And playing around with those identities. Let me give you an example. And I'm not going to do a lot of these, but I'll give you one example. Let's say we want to solve for, I'll do theta. Theta is between 0 and 2 pi. And I have 2 times sine theta times cosine theta is equal to 0. Okay. You should look at that, maybe, well, the easy way to do this, I'm sure there's harder ways. But the easy way to do this is to say, well, 2 sine theta times cosine theta equal to 0. Yeah, now that I think about it, there's actually a couple different ways you can do this, but let's do it. I'll do the way I was originally intending. Okay. 2 sine theta cosine theta, that's actually one of my trig identities. All right. If you look on your trig identity sheet, that is one of the double angle identities. And so I can replace 2 sine theta cosine theta with sine of 2 theta. And now I'm back to doing the exact same thing we started with, right? Sine of something equal to 0. That means that something has to be like negative. It's integer times pi plus I'll just say the integer times pi, right? Yes. Let's see. So negative 2 pi, negative pi, 0, pi, 2 pi, 3 pi, 4 pi, 5 pi, et cetera. Divide everything by 2, and then just take the numbers between 0 and 2 pi. If I divide everything by 2, I get that. And then if I'm only taking the numbers between 0 and 2 pi, oh, this one had an equal sign. So I guess I'll include the 2 pi. If it didn't have an equal sign, I would not have included 2 pi. Does that make sense? So I threw a double angle identity at. That's basically it. And so there's a bunch of different things you could deal with. things like that. Now, before I do another one where we have to use that identity, I want to solve this. Let's just say solve for theta. Between 0 and 2 pi. Remember I said earlier that we're gonna treat our trig function like a variable? That's what we're gonna do here. So if you have x squared plus 6x minus 7 is equal to 0, hopefully you'd factor that. Does that make sense? So we're gonna treat this like, I don't know, I'll use C for sake of argument. And hopefully we factor -7 into a z minus 1 times a z plus 7. Let me rephrase that. Factors of -7 that add up to a +6 are -1 and +7. -7. Those add to a +6. So in the same way we factor that, we would factor this. We would say factors of -7, -1, +7. So I do cosine of theta minus 1 times cosine of theta plus 7 is equal to 0. Over here, what I would do is I would then set each component equal to 0. And then I would solve each component, right? Well, that's what I'm gonna do here as well. I'm gonna say either cosine of theta minus 1 is equal to 0, or cosine of theta plus 7 is equal to 0. Remember, that only works with 0, right? We had to have 0 on the right-hand side to actually be able to factor, and then use the 0 factor property. That's it. Now, here's the thing. when I factored with just a variable equal to a number, I would be done at this stage. However, when I have cosine theta equal to a number, then I have to turn back to all the stuff I was doing just a second ago and say, okay, now what angle gives me cosine of 1? So you can do the theta equals inverse cosine of 1 if you'd like, or you can think back to the unit circle. The angle that gives us 1 is 0, angle 0. By the way, if you project this across the x-axis to get your other angle, it doesn't project across the x-axis, it's on the x-axis. That makes sense. Let me draw what I was talking about. So if we have a unit circle, what we got there is that point over there on the right. Angle 0 gives me that point. Projecting across the x-axis doesn't move that point. I guess you could do 2 pi minus that, but you just get 2 pi, which is, we didn't include that 2 pi. So the only answer I get from this left-hand side is theta equals 0, or theta equals 2 pi plus 0, 4 pi plus 0. Let's get the point. Okay. Same value. Now on this other one, if you say, well, therefore, on this other version, theta is the inverse cosine of -7. That's a does not exist version, right? Cosine can only be between -1 and +1. So this theta does not exist. So we don't get any answers from this side. The only answer we get is coming from this side. So this only has one solution, and that's when theta is equal to 0. Does that make sense? So if we have a quadratic, we can solve it like this, basically. We just factor it normal, and then we get a linear with cosine, another linear with cosine, and we're off to the races. So now let's combine both ideas let's say I have 4 times sine of theta is equal to 4 plus cosine squared of theta. All right. Notice that there's a mixture of sines and cosines here. I don't like that, right? Hopefully we don't like that. I'd rather have something like all cosines, or all sines, or all tangents, something like that. So in order to get, and when I say all cosines, it's all cosines of the same argument. I don't want to have like cosine of 2 theta and then a cosine of regular theta. Okay. So anytime I see something like this, a mixture of cosines and sines, I say, let's change these all to sines, or let's change these all to cosines. Changing a sine to a cosine is not very easy. But changing a cosine squared to something else involving a sine squared, well, I can do that with my Pythagorean identity. So if I use my Pythagorean identity, since cosine squared plus sine squared equals 1, if I subtract sine squared from both sides, it'll say cosine squared is equal to 1 minus sine squared. You okay with that? So this is coming from the Pythagorean identity. Cosine squared of an angle plus sine squared of an angle is equal to 1. And so I can replace the cosine squared of an angle with 1 minus sine squared of same angle. That makes sense? So I replace my cosine squared with 1 minus sine squared. And then I'm gonna algebra. Apply some algebra. Add like terms, you get 5 minus sine squared. And then now I have a sine and a sine squared. I'm gonna force it to look like that. I'm gonna force it to look, I'm gonna add sine squared to both sides. And I'm also gonna subtract 5 from both sides. So I can get it into a format that looks like a quadratic where my variable is sine of theta. And just like I did on this one, that earlier one, I say let's factor. Factors of -5 that add to a +4 are -1 and +5. It's gonna turn out very similar to the last one, right? That we did. So we get sine of theta -1 times sine of theta +5 is equal to 0. With my first factor equaling 0, I get sine of theta equal to 1. And if I do inverse sine, I get that my theta is equal to pi over 2. And just like before, if you project across the y-axis with pi over 2, you get to pi over 2, right? So projecting across y-axis doesn't give you anything new. Doesn't change theta. Remember, projection across the y-axis is pi minus the value. If you do pi minus pi over 2, you get back pi over 2. All right. Over here, we're taking sine and getting a -5. So that does not exist. That gives me no values. By the way, that just means the answer is this single value of pi over 2. Okay. This doesn't leave anything that's bad. This does. Or I should say bad. This doesn't leave any solutions. This leads to one solution. Oh, I started to say that. Is everybody okay with this? So I used the Pythagorean identity there. And then that gave us a quadratic. And then I could solve that quadratic. Now, these two that I've given you, obviously I've solved through factor. Okay. But you could imagine, and I tried not to give you these on the test, but you could imagine a scenario in which you couldn't solve via factor. Maybe you get a scenario that's something like, let's just do this, 2 times tangent squared of theta plus 3 times tangent theta minus 6 is equal to 0. I don't think that one factors. I didn't check it. But let's just say it doesn't. Let's say we can't see that if it factors or not. How would I figure out what tan of theta could be in this case if I end up with a quadratic that I can't see if it factors or not? Well, we could still use the quadratic formula, right? But instead of saying x is equal to opposite of b plus or minus the square root of b squared minus 4ac all over 2a, I instead say, well, the tangent of theta is equal to opposite b plus or minus the square root of b squared minus 4ac all over 2 times a. And then this is gonna give me 2 equations for tangent. I'll go through the whole thing. Well, I'll go through the whole thing until I get down to tangent equals those 2 numbers. Opposite of b would be -3 plus or minus b squared would be 3 squared minus 4 times 2 times 6. I'm sorry, times 4 times 2 times -6. Excuse me. All over 2 times a, that's 2 times 2. Sorry, my c was a -6. Initially said that was a. It was a -6. Okay, so let's see what's underneath that square root. So I get the tangent of theta equals -3 plus or minus the square root of 57 over 4. Is that right? Now, how would I solve that? First off, I have 2 answers there, so I'm gonna separate it into 2. Equations. And then I'm gonna solve both using inverse tangent. I gotta be real careful about how I type it in. I get about 0.85. For my first answer on this equation. We could also project through the origin. Remember projecting through the origin, that's the easiest one. Adding pi to that. And that gives me an angle of about 3.99. So I got two answers from this equation. Everybody okay with that? Let's check out that other equation. I initially get an angle of about -0.121. That's not between 0 and 2 pi. So the first thing I'm going to do is project through the origin. Which is adding pi. And then I'm going to make it a positive. By adding 2 pi to the original. We're gonna get that. So I take my angle, that -1.21, and I add pi to that. That gives me about 1.93. And then I'll make it a positive by taking my original angle and adding 2 pi to that. Which gives me about 5.07. And if you go through every single thing and check it out, you can obviously plug it back into your original to check all these, but you end up with 4 solutions. Between 0 and 2 pi. And they're right there highlighted on the board. Now that's a fairly long problem, but anybody have any questions over that each individual component? We've basically made it a quadratic with tangent being our variable, tangent theta being our variable. And then we solved using the quadratic formula. And then once we have our variable equals those two numbers, then I have to do the additional step of solving what we did the first hour and a half of class, which was I had a trig function of a theta equal to a variable, solve for theta. And I had to do that twice because, well, we had a quadratic to start with. So we ended up with 2 of those. But essentially, just like solving 2 things that we did earlier. Now, I can't give you all of the things that you're gonna need, but I will say this, if you look at, actually, let me download. I think I've already done this download the trig identity sheet, but yeah. But if you look at the trig identity sheet, and I'm gonna highlight just a couple of places. A couple of places that quadratics come into play. So you'll see that quadratics could come in through Pythagorean identities. We did one of those already. If you have double angles, you can also get quadratics through this. Cosine of 2x is equal to 2 cosine squared minus 1. And also cosine of 2x is equal to 1 minus 2 times sine squared. And also cosine of 2x is equal to cosine squared minus sine squared. There. By the way, think about if I saw a cosine of 2x, if the other part of my equation had a cosine in it, I would probably think, oh, that's going to be a quadratic with cosine squared. Does that make sense? If the other part of my equation had a sine in it, I'd probably think, oh, that means I should probably use the sine squared. Does that make sense? Here's what I'm going to do. I'm going to bring some up and kind of give you a hint on one of the problems on the homework. Keep forgetting which one it is. Oh, no, that's that one. Yeah. So if you look at this one on your homework, here I have a cosine of 2x, and I also have a sine of a single x. So when I use my double angle identity on the cosine of 2x, I'm probably going to be using this one so that I'm dealing with sines and a quadratic in sines. Does that make sense? I probably will not use this one because then I'd be mixing cosines and sines again. All right. So it's those little things that sometimes you have to choose and be a little bit conscious of. Obviously, you could use any types of identities. Some of those are going to be better than others. Let's think through how do I want to say this? sum to product, product to sum. Oh, there are some that you may be able to immediately go through. Let me give you an example of what I'm trying to get at. So let's take something that looks like the sum to product identity, all right? That says sine x plus sine y equals this. Let's say I had sine of 3x plus sine of 4x equal to 17. Some people may want to use a sum to product identity right here. But let me tell you why you might not want to use that. How big could sine be? Well, sine can be between -1 and 1. No matter what the angle on the inside is. So if sine can be at most 1, and we're adding two sines together to give me a 17, something's off, right? So rather than jumping to the sum to product identity, you might want to say, well, the sum's at most 2. Therefore, we can jump straight to does not exist. Everybody okay with that? Now, that's not the only thing that you may run into. Obviously, there might be a scenario in which you have sine of, let's say, 3x plus sine of 1x equaling 0. That absolutely can happen. Remember, the sine has to be between -1 and 1. And therefore, you could have things that add together and cancel out and give you a 0. So you could apply the sum to product identities here. So you go on your sheet and you apply the sum to product and you get 2 times sine, and then I have to add the angles up and divide by 2. That, everybody follow that? 3x plus 1x is 4x, divided by 2 is 2x. And then cosine I'd have to subtract and divide by 2. 3x minus x is 2x, divided by 2 is 1x. Everybody understand where I'm getting that identity from? Alright. That's my sum to product identity. And this is something that might not look pretty right now, but I have things that are being multiplied to give me 0. So in this special instance, I can say, well, that means either the sine of 2x has to be 0, or the cosine of x has to be 0. And I know when those things are 0, right? Okay. Oh, did we? I didn't specify, but we'll probably go from 0 to 2 pi again. 0 to 2 pi. When I divide by 2, give me 0 pi over 2. 2 pi over 2 is pi. 3 pi over 2. Divide by 2, you get 2 pi. Depending on whether I'm including 2 pi or not, I include it or not. Are you okay with that? And if I go over here, 0 to 2 pi, I just get those answers. Right, 5 pi over 2 is larger than 2 pi, so. And notice that I got some repeats here, so I actually only have 4 answers when I combine the 2 answers together. So when I combine these 4 with these 2, I still get 4. Pi over 2 exists in both solutions. Is all this making sense? I was trying to be really, really thorough on 7.5, okay? Because there's a lot of different ways that these trig equations can look. So I'm trying to do, I tried to originally do some with cosines, some with sines, so that we projected across the x-axis, then projected across the y-axis. Did some with tangents, so you project through the origin to get your other answers. Do some with trig identities, some that did not exist, some that did exist. Here we have trig identities. Sometimes we have trig identities plus quadratics. So we have quadratics and trig identities plus quadratics. All kinds of stuff. So lots and lots of different versions. Okay. The vast majority of problems that I give you are gonna be more like the ones that we did for the first hour and a half of class, where it's trig can be solved to give you trig function is equal to a number. All right? And then you do the inverse trig function of that number to get the angle. And depending on whether you use sine, cosine, or tangent, depends on how you project. If you use cosine, project across the x-axis, 2 pi minus your angle. If you use sine, you project across the y-axis, that's pi minus your angle. And then if you use tangent, you project through the origin, which is just adding pi. And if you ever get a negative angle, want to make it positive, add 2 pi to it. Most of them are that way. And then some of them are these ones, where you have to use a sum product identity. Or you have to use a Pythagorean identity, or a double angle identity. And then you solve it using zero factor property, or quadratic formula, or something like that. Okay. Any questions about that? Now, I know we only have a couple of minutes left in class. I didn't originally plan on going that deep into 7.5, but it's nice that I did, because that's most people, chapter 7 is the hardest chapter for most people. Okay. Now, we are also going to cover chapter 8, and we'll do this pretty much all next time. Chapter 8 is all about solving triangles. And so it's going to look like solving triangles similar to what we did with right triangles, but we're not going to have right triangles. We're just going to have any triangle. Does that make sense? And so we're going to have two tools where SOHCAHTOA only apply to right triangles, and the Pythagorean theorem only applied to right triangles. Well, we're going to have two theorems that are going to apply to any triangle. One's called the law of sines, one's called the law of cosines. With those two things, we can solve any triangle we want. Does that work? So that's what we'll do next time. And yeah, I don't think I'll get started on that today. Okay? We'll just do all of chapter 8 next time. Okay, on Wednesday. Most people like chapter 8. After we get through chapter 7, chapter 8 is gonna be like, oh, now I'm back to solving triangles, and this is like the nice stuff. Just 2 rules. Okay. All right. I'll see everyone next time. See you.